Hello, and welcome to the fourth video for section 4.3, where we're talking about analyzing functions for increasing, decreasing, and concavity. So this is part 4 of those videos, and we're going to pick up with example 4, where we talk about identifying the intervals on which the following functions are concave up or concave down, and then locate the inflection points. Now, when you see concave up, concave down, or inflection point, you should be thinking second derivative. So to make this video a little neater and go quicker, I've actually taken the derivatives below, but our function is f of x equals x times e to the minus x, and we're going to do this one with a product rule when we take the derivative. And remember, when I set up the product rule, I suggest that you separate out your two functions, write down their derivatives. And so when we do that, I'm going to scroll down and you're going to see for part A, down here, we get the first derivative, right here, is the derivative of x is 1, so it's 1 times e to the minus x, and the derivative of e to the minus x is negative e to the negative x, as I wrote up here, so that's where that subtraction comes from. You get minus x e to the minus x. You could have had it in the other order, negative x e to the negative x, plus the e to the negative x. Then I factor out an e to the negative x. I haven't made you simplify a lot for answers, but when you're taking second derivatives, you do want to simplify the first derivative by factoring if possible, because then it makes taking the second derivative easier. And again, the second derivative right here, you have to use the product rule again. I have the first function is e to the negative x, the second function is 1 minus x. The derivative of the first function is e to the negative x. The derivative of the second function is negative 1 from the subtraction in front of the x there. Then this subtraction comes from the fact that the derivative of e to the negative x is negative e to the negative x, and then I have the second function. And then when I expand this out, it's a little tricky with the negative sign, so I did it all out here. I factor out an e to the negative x, and I had it times a negative 1, and then it was subtracted times a 1 minus x, so I get a negative 1 minus 1 is negative 2. The subtraction turns that x to positive. I get negative 2 plus x. So the second derivative is 0 at x equals 2. That's our potential inflection point. It is only an inflection point if the second derivative actually changes sign there, which it will. And we'll take a look at doing that. So to check if something changes sign, we often have used this tool called a sign chart, where you only write the zeros of the function on the chart in order as if they were on a number line. 2 is the only one, so that's not an issue here. And then you test the value. For x less than 2, I can test the number 1, as long as that's, so this interval here is x less than 2, pick a number less than 2. This is x greater than 2, pick a number greater than 2. And I'm looking for the sign of the second derivative. So if I put in 1 here, I get negative 2 plus 1. I'll get a negative 1. And this value, exponentials, even though it's a negative exponent, that's always going to be positive. You never get a negative answer for an exponential. And that's the reason you can't take the log of a negative number. You never get a 0 or negative. So I've also ignored the e to the negative x for the zeros, because truthfully, when you do this out looking at both factors, you would do this and you would check both factors. But when you have an exponential as your factor, the answer to this is never, so it doesn't contribute to your zeros. And then this becomes negative 2 plus 2 would equal 0. If I just add 2 to both sides, I can see that too. So that's where I got the 2, and that's why I didn't consider the e to the negative x. And a positive exponential base raised to a power is never negative, and it's never 0. It might get very close, but it's never 0. So what I see here is when I plug a 1 in, I get a negative second derivative. Sometimes I just write a sign, and here I get a positive second derivative. Sometimes I just write a sign. So indeed, the second derivative does change sign there. So my inflection point occurs at x equals 2. And if I want the y-coordinate of that point, I have to find f of 2. I didn't continue doing that here, but it'd be 3 times 2 to the 4th. Oh, I'm sorry, I have the wrong function. X equals 2. My function was x e to the x, I believe. Let me look. Yes, it was x e to the x. So f of 2 will be 2 e to the, it was to the negative x to the negative 2, or 2 over e squared. So if I'm asked for the point, if I'm just asked where, they're asking for the x. If they want the value of the function there, if they want the whole point, I have to plug back into the original function. Because remember, f of x was x e to the minus x up above. All right, so that's part A. And we're going to move on and do part B. Let me see if I can clear this. I'm not as good with this tool as I am with some others. But no, okay, I'm not going to clear that all. Yeah, I guess I can. I'm going to clear all this, get this out of the way. You can always go back and look at the recording. That's the nice thing about recording. It's different than me being in class. For part B, our function started out as 3x to the 4th minus 4x cubed minus 6x squared plus 12x plus 1. So that first derivative comes out to be 12x cubed minus 12x squared minus 12x plus 12, and it's easy to pull a 12 out of that. Now I take the second derivative, and you can see why it was easy. When I take the second derivative, I get 3x squared minus 2x minus 1 in parentheses. And it's easier to factor that than it would be to factor 36x squared minus 24x minus 12. You would want to factor that at that point. So factoring first is easier. And this is just a constant times a function, so I could do the constant times the derivative. I didn't even actually need the whole product rule. So then I solve this. I solve this by doing 12 equals 0, which is never. That's one of the factors, but we ignore that because it's never equal to 0. And then 3x plus 2 equals 0. 3x equals negative 2, x equals negative 2/3. That's where I get that one. And then x minus 1 equals 0. Hopefully you all see that. That gives you x equals 1. So I have two values to put on my sign chart. And we don't, these are all well-behaved functions with all real number domains. But if I'm just looking for inflection points and I had a discontinuity in the second derivative, if I had a place where it didn't exist, you don't consider that to be an inflection point, because an inflection point has to actually be a point that exists in the domain of the function. You have to be able to find the y coordinate if you need to, if you're asked to. So negative 2/3 comes before 1 on the number line, so the negative 2/3, and these intervals represent negative 2/3 less than x less than 1, x greater than 1, and x less than negative 2/3. And I just want to see the sign of the second derivative to make sure it changes at each of these. So x equals negative 2/3. I'm going to pick x equals negative 1 to check that. When I put in x equals negative 1 to this is negative, this is negative. It looks like I get a positive. Is that true? Yeah, it would be positive. The other thing you can do is recognize that this is going to be parabolic. The second derivative is going to be shaped like that. So if you have the two zeros there, you know you're going to have a positive, a negative, and then a positive, if you remember that from your function analysis. So in the middle, I'm just going to put 0 because that's easy, and I get negative 12 out of that, so that's negative. And then if I put a 2 in for x greater than 1, I will get a positive value. So the inflection points occur at x equals negative 2/3, and you can put that into your original function to find the y coordinate. That original function is back here. 3x to the 4th minus 4x cubed minus 6x squared plus 12x plus 1. If you need the y coordinate, you could use your calculator to help you with that if you wanted to. And the other one is at x equals 1. If you need the y coordinate, put that back to the original function. But let's go back and make sure we answered the question. I did not answer the question entirely in either of these. It wants to know where's the function concave up, concave down, then find the inflection points. So I have already erased the work for part A, but we did have a nice little sign chart with an x equals 2. And when x was 0, for example, I had a negative value. So the sign of the second derivative was negative and then positive. So this is concave down. And we usually use interval notation, so that's from negative infinity to 2. And the 2 is not included because the second derivative is 0 at 2. It's not negative. And this is concave up from 2 to infinity. And again, the 2 is not included. So then for part B, I left our work here. So what we see is we have concave up because the sign of the second derivative was positive. So from negative infinity to negative 2/3. And also, we're concave up from x greater than 1, so from 1 to infinity. And concave down. And again, none of these endpoints are included, negative 2/3 to 1. Okay, so that's those two examples. I'm going to do the student practice problem that's next, so you can try this and then pause the video and come back and see these. We're going to take a look at some things from the first derivative and the second derivative here. All right, so here we go. Parts A and B ask, where's the function increasing and where is it decreasing? So I've taken the first derivative, hopefully you got that far, and then I found the zeros. There are 3 of them. Often students forget that 0. So you've got one at negative 6, one at 0, and one at 6. So there's a couple ways to do this. You can plug in test points. At x is negative 7, this is negative, that'll be negative, that'll be negative, that'll be negative. 3 negatives multiplied together gives you a negative. The other thing you can recognize is that your derivative is cubic. Shape goes like this. If it's a positive cubic, the end behavior is like that. And you can kind of sketch the function. If you took pre-calc 1 with me, you certainly did a lot of this function sketching. Negative 6, 0, 6, and you can see I'm below the x-axis, less than negative 6, above it, between negative 6 and 0. So I'm going to pick a test point between negative 6 and 0. If you choose negative 1 and put it in, you will find you a positive. So I have a negative, a positive, and this is the first derivative I'm checking. This is the sign of y prime. If I put in x is 1, I am again negative because this will be a positive. This will be a negative, this will be a positive times a negative times a positive is a negative. And if I plug in x is 7, everything will be positive. So I do have this alternating pattern, which you will always get if you don't have any repeated zeros. If you have repeated zeros, that's where the signs won't change. So what I know is the function is decreasing where the first derivative is negative. So I'm decreasing on the interval negative infinity to negative 6. And again on the interval 0 to 6. And I am increasing, the function is increasing, from negative 6 to 0. Again, the endpoints are not included because at the endpoint, the derivative is 0. And then from 6 to infinity. Okay, so that's increasing and decreasing from the first derivative. Then we talk about concave up and concave down. So let me move concave up and concave down. We need the second derivative. So I have taken the second derivative here. I get 12x squared minus 144. I factored that to solve it. You get, you take out a 12 and you get x squared minus 12. So this goes to x plus the root of 12, x minus root of 12. You'll have 2 zeros. The 12 will never be 0, but this will give you negative root 12, and this will give you positive root 12. Again, you draw a number line. You go, oh, what's the negative root 12? Do it in decimals if you have to, but I'd like to believe you can tell that negative root 12 is to the left of 0, and positive root 12 is to the right of 0. Or, technically, it's 2 root 3. Negative 2 root 3. If you factor out the 4, that would be simplified. But in any case, so you say, well, negative root 12, well, you know, negative root 16 will be less. So I'm going to pick a negative 4 here. 0, I'm going to pick a negative 1. Here I'm going to pick a 1. Square root of 12 is going to be more than the square root of 9. So, you know, it's at least a 3. You know, this is like a negative 3 point something because the square root of 16, that would be negative root 16. So that's why I know negative 4 is okay there. You can use decimals, though, if you need to. So root 12, I'll just pick a 4 here also, because 4 will be root 16, which would be bigger than root 12. I plug these numbers back Oh, why did I get the 0? I made a mistake here. I said y double prime is, I read that as 0. There is no 0 there. So I just have to pick one number here in between negative root 12 and positive root 12, and I'm going to pick 0. So I check the sign of y double prime. Y double prime of negative 4 will be, so negative 4 plus root 12 will be less than negative 4. That'll be a negative number. That'll be a negative number. That'll be positive. The other thing you can do is realize this is a upward opening quadratic. So you've got one root, you've got the other. You're going to have positive on the ends. And if I do y double prime of 0, I will get a negative sign. And if I do y double prime of 4, I will get a positive again. 4 plus root 12, 4 minus root 12 will both be positive. So I get concave up wherever the second derivative is positive, and that's from negative infinity to negative root 12 right here. I found the second derivative was positive here, negative here, and positive there. And from positive root 12 to infinity. And then concave down was in the middle of that, negative root 12. And these intervals will never overlap because you can't be both concave up and concave down in a function at the same time. So that's C and D. Now we have our first and second derivative, and we look at this question here. We got A, B, C, and D. Then inflection point will be where a 0 of the second derivative where a sign change occurs. So it looks like we have two inflection points. The inflection points will be at negative root 12, f of negative root 12, and I'm not going to do that out. You would go back into the original function to find what that y value is, and root 12, f of root 12. That would be where the inflection points are on the function. On the function, you get that twisting from concave, in this case, concave up to concave down, and then concave down to concave up at root 12. I didn't draw that in the right place on the line there. So we've answered concave up, concave down. Has an inflection point. A local max. Well, a local max, if you have the sign chart for the first derivative, a local max looks like this. And over here, y prime is positive. Over here, y prime is negative. Now, the other thing you do is plug critical values into your second derivative, but we already have the sign chart. So the first derivative test is easiest. So a local max will occur where my sign changes from positive, my sign of my derivative changes from positive to negative. Looks like that happens here. And that's the only place that happens. That's at 0, f of 0. And the function was pretty easy to find. So that would be at 0, 5. Because f of 0 will be 5. And a local min, now there may be two local mins. It looks like I have, so that would be a local min looks like this. So y prime would have been negative, and then y prime would have been positive over here. So anytime I go from negative to positive, there's one, and there's one. And so I'm going to get x is negative 6, and then f of negative 6. I'm not going to take the time to do that here. And then x is 6, f of 6. There's your local min. And if they're just looking for the values of x, you only had to answer the 0 for the max, the negative 6, and the 6. I'm just saying if they ask for the actual point, you have to find both. You don't always have to find both. It says find the values of x, or find where the function is, these things. So you don't have to find the other half of the point for this question. I'm just doing it to show you that you will use the original function. An absolute max or an absolute min. This is where you have to take all the critical values, okay? And you only have one local max, so you know that's going to be, no, you don't know anything actually. You got to check that. So you would have had to find all these values anyway. You take the 0, the negative 6, the 6, and you find the y coordinates of them. And there was no closed interval here. If they had given us an interval, we would have had to check the endpoints as well. And after we checked those endpoints, we would take and look at all the y values for the critical. So for the absolute min or max, I make a little table, and I put all the critical values. So I would put -6, critical values as zeros or places where the first derivative does not exist. In this case, you do consider where you have domain issues. And then I would put the left end of the interval, the right end of the interval. And for all 5 of these, I would calculate y using the original function. And then the biggest y, the highest number, shows you the point of your absolute max, and the lowest one shows you the point of your absolute min. Okay. You can stop that and rewind. You can email me your questions. We're going to move on to the next question, which is a little more, I don't know, it's a little more abstract, so students have trouble with it, but it's actually easier. So this just gives you some information about the first derivative and the second derivative. It doesn't tell you about the function, but it also says it's continuous on, so the function's continuous, but notice the derivatives don't have to be, on the domain -2 to 4. So the left end of the most leftmost point you're going to have in an interval is this -2, and the rightmost point you can have in an interval, and the answer is the 4. All right. So first, I want to know where local maxima or local minima. I'm looking for a sign change from plus to minus in f prime. Or I could be looking for a critical value. So I'm looking for sign change from plus to minus. So the first derivative is positive there, but at x equals 0, it doesn't exist. And then it's negative. Now that could be some sort of a point. So the function's continuous there, so that you know that point exists. It's not a vertical asymptote, because we're told the function's continuous from -2 to 4. But you could have a sharp point, which would mean the derivative doesn't exist. So I would say the values of x where there's a local maximum or minimum would be at x equals 0 is a max. And I have a negative, but this is still negative. So that is x equals 2 is not a min. This would have to have been positive over here. There's no local min. So because there's only one local extreme, you know that is also the absolute max. But there's no local min. So points of inflection is where f double prime of x equals 0 and the signs change on either side. So f double prime of x does not exist here, and the sign doesn't change anyway, but even if it did, it wouldn't be an inflection point because the second derivative has to exist. Here's an inflection point. Notice on inflection points, we don't care whether it's plus to minus or minus to plus. That occurs, the 0 occurs at x equals 2 to the left. The second derivative was positive. To the right, it's negative. So that is at x equals 2. And this function is concave up wherever the second derivative is positive. So the interval will be from -2 to 0, but not at 0 because the second derivative does not exist there. And then from 0 to 2, but not at 2 because the second derivative is 0 there. If I were asked about concave down, I would only include from 2 to 4. Okay, and sometimes this is a round parenthesis depending on the interpretation of what you do with the endpoint. I will make sure you get credit for either in tests and quizzes. There's your second derivative test. We're going to talk about that in the next video. Okay, I will make a part 5 video to talk about that. But for right here, we've got examples of concavity.